Hello everyone, and welcome to the first video of this course. In this course, we will start by reviewing the fundamentals of FPGA design. In this video, we will review combinational logic, we will go over truth tables, Boolean equations, and see how both can be implemented directly in Verilog. Finally, we will learn how to implement a 2-to-1 and 4-to-1 multiplexer using the Ternary operator. The most fundamental kind of digital circuit is a circuit whose behavior can be modeled in a table, commonly referred to as a truth table. Below is an example of a truth table describing the behavior of a combinational circuit. If we set ABC to 0, 0, 0, then the output should be 0, since that is how the behavior is defined in the table. If we set ABC to 0, 1, 0, then the output should be X, meaning we don't care what it is. If we set ABC to 0, 1, 1, then the output will be 1, since that is how the behavior is defined in the table. Anytime we have a truth table, we can convert the table into Boolean equations. From those Boolean equations, we will have an optimal and compact way of describing the digital circuit. So how do we convert a truth table into a digital circuit? Well, this process is done with a tool called a K-map. A 2-input, 3-input, and 4-input truth table will all use a specific K-map. The overall process of converting a truth table into a digital circuit comprised of logic gates is shown below. For any two-variable truth table with inputs IN1 and IN0, we will always use the following K-map. For any three-variable truth table with inputs IN2 to IN0, we will always use the following K-map. For any four-variable truth table with inputs IN3 to IN0, we will always use the following K-map. So now let me show you an example of how a three-variable truth table can be converted into a digital circuit. So the first step is to identify that we need to use a three-variable K-map. The second step is to map the 1's and x's to the K-map. The indices make it obvious where each 1 or x should go. The third step is to circle the terms. When circling the 1's and x's, we can only circle in groups of 1, 2, 4, 8, and so on. Also, we cannot circle diagonally. Ideally, we circle in such a way that we have the fewest number of large circles. The second part of the third step is to generate the terms and equations. For each circle, we write down the circled indices and generate the terms. If an index changes, its term is dropped. If it remains a constant 1, the term is used directly. If it remains a constant 0, the inversion is used instead. After we have generated all of the terms, we can obtain the equation by ORing them together. After generating the terms and combining them into one equation, we get the following expression for D. The final step is to convert the Boolean expression into hardware. This digital circuit implements the exact behavior defined in the truth table. In the previous example, you were given a good refresher on the entire process of taking a truth table and performing the 4 steps to get a schematic of its equivalent digital circuit. Now on average, it takes maybe 5 to 10 minutes to solve any K-map by hand, so it can be time-consuming. Fortunately, in Verilog, you have the flexibility to implement a truth table with a high-level description. By using Verilog, you can create a digital circuit in a fraction of the time it would have taken otherwise. The thing that is great is that no matter what the table, the Verilog-based truth table approach is always extremely fast and quick. This example shows how a truth table can be implemented directly in Verilog. By using a combinational always block, we can implement the truth table without needing to manually solve for equations. This here shows another example of how a different truth table can be implemented in Verilog. The great thing about this approach is that the methodology never changes, regardless of the truth table. Just to make it super clear, here is a third example of a 4-variable truth table being implemented directly in Verilog. Again, the truth table was implemented using the exact same approach as the previous examples. Although Verilog-based truth tables are extremely quick, efficient, and easy to deploy, Verilog's syntax allows you to implement Boolean equations too. Here are the Verilog operators. Also, once you have a Boolean equation, implementing it in Verilog is very easy. The following examples show this. This example shows how to implement the Boolean expression for z in Verilog. This example shows how to implement the two Boolean expressions in one Verilog module. So the final thing to discuss is the Ternary operator. The Ternary operator is a question mark paired with a colon. The Ternary operator is used to implement combinational muxes in a single line. The example below implements a 2-to-1 multiplexer. When select is equal to 1, out is equal to input 1. When select is equal to 0, out is equal to input 0. By nesting two ternary operators, we can implement a 4-to-1 multiplexer. The example below shows this. Alright, so we have now finished our review of combinational logic. We reviewed truth tables and Boolean equations, learned how to implement them directly in Verilog, and explained the ternary operator. In the next video, we will review sequential logic. Alright, thanks for watching, and I'll see you in the next one.